Hello, myself Abhishek Chaudhary, and in this presentation, I'll be explaining about Turing machine and its applications. This is the agenda of the presentation. So, first, we'll talk about Turing machines. Turing machines are a mathematical model which was invented by Alan Turing in 1936. This is a very important concept in theory of computation. And they accept recursively enumerable languages, which are languages which can be generated by type 0 grammar. This is what a Turing machine looks like. Consists of an infinite tape with symbols on it, and there are discrete cells. Each cell contains a symbol, and there is a read-write head with a finite control. This read-write head reads the symbol from the tape, and it can write the symbol onto the tape. So at every step of operation, it will read the symbol, write a symbol onto the tape, and will move either left or right. A Turing machine can be formally defined with a seven tuple Q, sigma, tau, delta, Q naught, V, and F. Q stands for the set of states in the Turing machine. Sigma is the set of input alphabets. So these are the alphabets which are present in the input string, and excluding the blank symbol. Then we have tau, the tape alphabet, which are the alphabets which the tape can contain. So obviously it has the input alphabets as well, and it also consists of the blank symbol and symbols which can be written onto the tape even if they are not in the input string. They are all part of tau. Then we have delta, which is the transition function. So which tells us for a particular state and given input, which state the Turing machine should go to, what symbol to be written on the tape, and whether the head is to move left or right. And Q naught is the initial state, B is the blank symbol, and F is the set of final states. So, for example, in this example, the 0, 1, 2, 3, 4, 5, 6, 7, and SF, these all are the states. So these are Q, and 0 is the initial state, so it is Q naught, and SF is the final state, so it is part of F. There can be multiple final states as well. So final state would be a subset of the state, and at every operation we will read a symbol, write a symbol onto the tape according to the transition function, and we will move either right or left. And there are many different variants of Turing machine, like multi-head Turing machine. So instead of one read-write head, there will be multiple independent read-write heads in the Turing machine. Then we can have multi-tape Turing machine. So there will be multiple tapes, and the head will work on all the tapes simultaneously. It will read from all the tapes and write value on all the tapes, and will either move left or right. Then we can have multi-tape, multi-head Turing machine. So we can have the multi-tape Turing machine, and then every tape will have its own independent read-write head. So it will be multi-tape and multi-head Turing machine. We can have multi-dimensional Turing machines. Instead of having a one-dimensional tape, we can have a two-dimensional tape, like a matrix, and the head can move left, right, up, or down. We'll have four options. And non-deterministic Turing machine. So for a given state and input, instead of having only one transition possible, there will be multiple possibilities for the Turing machine. All these different variants will have the same computational power. We have first Turing thesis. So this states that any algorithm can be converted into a Turing machine. So if for a problem we are able to design an algorithm, we can make an equivalent Turing machine for that. Working of a Turing machine can work both as an acceptor and as a transducer. So it can either check if the string is of a particular kind or not and accept or reject it, or it can convert the given input string into a required output string. We will start with the input string on the tape, and the head will be pointing to the leftmost symbol. This will happen in both the cases. And then we will read the symbol, and according to the transition function, write a symbol onto the tape, and will move either left or right. We will keep repeating this process, and then until we reach a halting state. So in acceptor case, it will be accepting or rejecting state, and in transducer case, it will be output or error state. So for acceptor, if we reach the accepting state, it will accept the input string and then halt. And for rejecting state, it will reject the input and then halt. For transducer, if we reach output state, it will produce the output string and halt. If we reach error state, it will halt, but no output string would be produced. universal Turing machine. So this is a Turing machine which can simulate any given Turing machine. So we will give the description of our Turing machine to the universal Turing machine, and then the input will be given, and then this universal Turing machine will imitate the Turing machine whose description we gave it. Halting problem. Halting problem. So when we were talking about acceptor and transducer, I told about halting state, the state where the Turing machine halts. But the question is, will the Turing machine ever halt? Will it reach the halting state? So that's what the halting problem is. For a given Turing machine M and an input string W, does M halt when run on W? This is an undecidable problem. There is no algorithm or no Turing machine which can solve it for all possible inputs. For a particular input, we can do hit and trial and we can predict, but for all possible inputs, there is no algorithm which can accurately decide if it will halt or not. This was proved by Alan Turing. So the proof involves assuming that there is a Turing machine which can predict, called the halting machine, and then we will give the input to it. But then if it does not halt, we will possibly halt it. So if it is not halting, we will make it stop. But if it does halt, then we will put it in an infinite loop. So this way, the results can be flipped. And so if we design an algorithm, this proves that it will have errors. It cannot be 100% accurate. And we have application Turing machine. So these are all the different applications. Turing machine, complexity studies, neural networks, compiler design, chemical computing, quantum computing, genetic engineering. There are more applications as well. So complexity studies, as we discussed, we can if we have an algorithm, we can design a Turing machine. Using that Turing machine, that equivalent Turing machine, we can analyze the computational complexity of the given algorithm. So we can figure out how much time and how much memory it will use to solve a particular problem using that equivalent Turing machine. And we have neural networks. So neural networks is a very important concept in machine learning, and that also can be implemented using neural Turing machines. These are recurrent neural network models which use augmented memory. They combine the pattern matching ability of neural networks and the programming capacity of Turing machines. We have compiler design. Turing machines are very helpful in compiler design. They can be used for syntax analysis. So we can parse the code and check it against the grammar of the language to check for errors. Semantic analysis. The semantics of the code can also be checked using Turing machines. This helps in uh, checking if the code is logically correct or not. Then code optimization. So for the translated code, we can optimize it using Turing machine. So, um, without changing the output or the side effects of the code. Chemical computing. So Turing machines are used to make chemical computers. Chemical computers are basically vats of chemicals which use chemical reactions to store and process data. And an example of this can be DNA computers, which use kinds of DNA molecules as its basic units of computing. Quantum computing, Turing machines are also used in quantum computing. We can make quantum Turing machines which provide a model which can which has the all the power of quantum computing. And Turing machines are useful in genetic engineering as well. They are used to design and optimize DNA sequence. So this is helpful in gene therapy and so. But this basically means that we can create a DNA sequence with any particular property which we want. Like for example, minimal length or maximal diversity or optimal folding, etc. That is my presentation. Thank you.